Today I'm going to be presenting on a tool for the validation of epigenetic datasets developed by myself, Jessica Shields, and Eilish Hannon from the University of Exeter. Robust datasets make for more reproducible and rigorous research. I think that is widely accepted. This tool, chromTools Complete, allows researchers to validate an epigenetic dataset, assessing the reliability of input data to downstream integrative analyses. The tool has been developed specifically for use with chromatin state annotation algorithms such as chromHMM or Segway, though would also be applicable to other peak-called datasets. Chromatin state annotation algorithms are a powerful tool to understand regulatory activity across the genome. These methods integrate different epigenetic data types, like the ones shown in these tracks here, and annotate the genome based on the combination of marks present at each position. Let's say that it is known that this region of the genome, where you see this combination of marks, is actively regulated. Using the annotation, you can therefore infer the regulatory state of each position of the genome at which this combination of marks is found, and this becomes particularly powerful when extrapolated genome-wide. However, the reliability of the annotation is affected by the degree to which the underlying datasets represent a complete set of marks. chromTools Complete has been developed in order to allow researchers to assess the completeness of their datasets. It can be used with CHIP, whole genome bisulfite, and ATAC data, and fits into a bioinformatic pipeline post-alignment requiring aligned bed files as input. The tool works by essentially concatenating these input bed files. It then subsamples based on a random subsampling algorithm, retaining a user-specified increment of reads. Let's say you have a 1,000 read dataset and you select an increment of 200. This would produce 4 files of 200, 400, 600, and 800 respectively. Each of these files is then binarized based on the chromHMM binarization algorithm, where the mark is deemed as absent or present dependent on the signal compared to a Poisson background distribution. The tool then calculates metrics and outputs 2 plots, one the proportion of marks compared to total reads, and the other a saturation curve with the expected maximum proportion of marks given that data set is also supplied. This is 2 example plots from the outputs from the tool. Looking at the plot on the left, you can see that with each increasing increment of reads, there is a gain in information, but with diminishing returns up to a plateau. This, combined with the plot below, where you can see that this expected max proportion of marks is close to the actual observed proportion of marks, would lead you to conclude that this dataset is reasonably complete. By contrast, the plot on the right shows that with each increasing increment of reads, there is an almost equal gain in information with no indication of saturation. This would lead you to conclude that more data would therefore be required to understand the pattern of this epigenetic mark. The calculated max proportion is also unlikely to be correct here, as there's not enough information in the data to accurately calculate it. Looking now at a published dataset, where the authors used chromHMM to annotate regulatory states across colorectal cancer tissue based on these 5 histone marks, you can see from the output of chromTools Complete that 3 of these datasets appear to be nearing saturation and therefore will be useful in differentiating different chromatin states. However, 2 of these are not appearing to reach saturation, and therefore you might conclude that it is unlikely that they will be informative in differentiating chromatin states. In summary, saturation curves are used to validate count data, such as RNA-seq or microbiome data, and are used to validate sequencing depth. This is the first application that we know of to allow researchers to validate an epigenetic dataset. Thank you for listening.